Welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. During the last two episodes, we've been talking about the Dixon method. Now we will introduce two additional optimization for it, and it will turn into a blazingly fast quadratic sieve algorithm. Hello, quadratic sieve. Okay, so what is that sieve that everyone talks about? Let me show it to you by an example. Let's assume that we want to factor this number. We're starting with the square root plus I, and we are going up mod n, and we try to see what of the values are going to be bSmooth. Let's assume this is our prime base. We want to see what of those values is going to be divisible by our prime base. So I prepared an example for it. Those are the mod n results of that value. And let's see what happened with that value mod 5. So for I1, it's divisible. And then plus 5 for 6 is divisible. Plus 5 for 11 is divisible. There is a cycle of 5. During each cycle, there are two divisible points on 1 and 4, and then plus 5 it's also divisible. So 4 plus 5 is 9 is divisible, plus 5 it's 14 is divisible, and going forward. With mod 7, it seems that none of it is divisible. It means that it's not even needs to be in our prime base. 17 also have 2 points on the cycle of 17. So I wrote it here. This is the cycle. You can see that 7, 14, 6, 0 is repeating here. 7, 14, 6, 0. Okay, so how can we find if the number is indeed needs to be inside our prime base? So it's a little bit a mathematical question, and I'm not so good with mathematics. So I prepared the solution for it. It's a class called messutils, and the way to do it is by using error criterion. It's the question is whether the value is quadratic residue mod n, and Euler criterion is a very fast way of finding it. Legendary symbol is yet another name. So this is how it's done. All right. So it helps us to eliminate those two values. If we have our cycle, let's say 17, and we are going to have some range of values. Let's talk about how we are going to do it. I'll talk about logging in a moment. So with the sieving process, we will pick a range starting from square root of n and iterate over that range of values. So it's kind of going to be an array. And inside that array, we will have all those cycles. I'm calling them wheels. So we will have wheels for each of our prime bases. And during the wheel of 17, it will mark all the numbers that needs to be divisible by 17. The wheel needs to know where to start from. We are going to have a very large prime in our base, and calculating them manually will take a long time. The fast way of doing it is by using resolve. It's a Tonelli-Shanks algorithm. I'm using a Butcher implementation, and I made some minor modifications to it. So by calling that method with the prime, and the end that we're trying to factor and the position we are starting from, it will return, in case of 5, 1, and 4, the indexes of where to start from. In case of 17, it's going to be 3 and 8, the indexes of the divisible items that we need to start from. Cool, so this is how we are sieving. Now, we still need to remember all the numbers that we are dividing by, and that again can slow us down. The log approximation solves that problem. Instead of doing the expensive multiplication, we will be doing log A plus log B, using doubles instead of big integers. It's a space win, and the operation is much faster. So on our during our sieving process, we will not be saving the values that factor a particular index, but rather we will be adding a log for those indexes. And if the log is bigger than some threshold, the threshold is the log of root n, or the beginning of our range, then the value must be bSmooth. Okay, so let's do it. In episode 5. Oh, and if you got any questions, please ask me in the Facebook group or comment below. The source code is going to be available on GitHub. And let's go. Okay, so I learned how to create classes. The shortcut for it. So it's going to be episode 6. So we are starting with building a prime base. And then we need to build our wheels. Okay, we'll implement it later. After that, we are searching for the smooth values. Let's log it when we are done. All right. And here's the prime change. So we are starting, we need a position. It's going to be square. That's fun. And then we can have a while loop where we've been doing something completely different. So first we need to define a range. Let's say our range is going to be, let's also work with big integers. It's going to be 10K. And play with those numbers later on. And then our position will increase by that range each time. We also need a logs array of the size of the range. And now let's create the wheels. So let's start with creating the class for it. And let's put it in a package wheel. And let's create a list of wheels. And now we can iterate over the wheels. And during each loop, we will update our logs. After updating the logs, we want to see if it beats the threshold. So let's define a threshold. Let's say that during each iteration, our threshold is going to be log. This is our threshold. Actually, it's not position. It's position power 2 mod n. Now we are doing this operation once, while in every 10 key values, versus in previous implementation where we did it for each value. Okay, so this is the base log. We are updating the wheels with the logs, with those logs, and after that, we need to see what of those logs beats the threshold. So logs I minus base log is bigger than base log. If it's bigger than base log, then for sure it must be a bSmooth value. So let's add the bSmooth value here. A. So A is the position plus the I. So and let's call it a local position. And B is going to be local position power 2 mod n. Actually, it's subtract n because when we are getting into square 2n, the mod will go back to smaller values. So subtract will keep the difference constant. Okay, and then the vector. So for the vector, we don't have to calculate it now. We can calculate it later on. So let's just leave it null for now. We found the bSmooth value, and if we found more than b such values, then we are done. Awesome. The question is, who is going to reset the logs? Let's add it here. Logs I equals no equals 0. Great. Now we can implement the wheels. So, or even before that, prime base. So now we are not going to add every prime to our prime base, but we're going to check mass utils. Is rooting quadratic residue, and we need to give it n and p. Can you be nice and just work? Yeah, I hope it did the magic. So if the condition is met, then add to prime base. Our prime base only includes the value that we added. Let's log it. So after building let's log it here. For building the prime base, log build prime base of prime base size out of b values, and max prime base size minus 1. Something like that. After we build our prime base, we can build the wheels. So for each prime in our prime base, we can build a wheel. Let's initialize that with a list first. Okay, so it needs a prime. And it also needs answer that question. So prime long value, and we need the position of each of those primes. And the position. The position is, let's get the position. What's the initial position where we are starting from? And that gives us those positions. So let's create a wheel for each of those positions. We have the prime, and the array size can be either 1 or 2. So we give it the prime, we give it the position. It can start from going from that position. Maybe it's all what we need. Starting position. Let's see. This is our starting position. For our prime, it's going to we're going to increase iterate. Let's start with implementing the update. It will be easier to see what we need. So we need to update the logs. We need to start with starting position. Actually, just use the starting position. And then our starting position needs to increase by prime each time. So prime equals to prime long value. And don't be final. Okay, and then we can update the logs at starting position to be the log value. So we need to add the log. So the log equals to log prime. And here, why is it? Can we change it to integer? I think it will work. I think it should work. So starting position can be bigger than integer, and then it will not enter the loop. But after it got out of the loop, then we can say that starting position equals minus logs. Thanks. It will be ready for the next loop, and then in here it will always be of the right size. Yeah. Cool. Maybe finals. I think this is it for the wheel. Right? So we created a wheel for each position. Up with me and spelling positions. Uh, oh, because we already have position defined. Okay, that's the BP. Cool. So we build the wheels. And now we need to extract the vectors. Let's do that. Oh, we need to provide position here. So the position is going to be n square and 1. This is our starting position. I think we're also using it in here, so let's be consistent. Yeah. Cool. So build wheels. Find bSmooth values. And after I found them, extract vectors. For each bSmooth value, actually it could be that some of our extraction will fail, that we may have some small mistakes on finding those bSmooth values. So let's protect ourselves and just create additional list for it. So we will just update the bSmooth with the list that we found. Extract vector from smooth b. If vector is not null, then bSmooth add vector, not add vector, but vector equals to vector. It's public, so what up? Oh, sorry. Then smooth vector equals vector. Cool. Let's log it. Head. Um, size out of bSmooth size vectors. Right. And I think this is it. Let's try. Okay, let me check this. Yeah, so the way that the wheels are working is that item is always of the size 2, but may have p's that are equals to -1. So we don't want them. Just want the actual values. Let's try again. Checking. Okay, two small things. So in here it needs to be -log, and in here need to add the vector. Cool. So let's try now. Yeah, we got the solution. It's working. Okay, let's go up. To go up, we also need to increase the prime base. So let's go to 100. Yeah, let's be brave. Yeah, 5 seconds. Okay, we can do faster than that. Let's go higher. Let's say 130. All right, 35 seconds to find the solution. For 130, that's big. I actually want to show you another optimization during this episode. Yeah, so for our base log, we can actually make the condition a little bit weaker. Instead of looking for values that are in that range, we can subtract from it in prime base get base size 1, because even if we have a reminder that we are not being able to factor with our prime base, that reminder can still be in our prime base, so it will be extracted. So let's try again. Yes, third of the time. Oh, awesome. So by getting more primes, it actually makes the algorithm much faster. More bSmooth values. Cool. So I hope you enjoyed this episode. We're starting to get some really fast and big numbers. I bet we can go even higher than that. If you have any questions, please ask me in the Facebook group or comment below. I will upload the source code to GitHub. I hope you enjoyed this episode as much as I did. Been waiting for it for a while. See you next time. Bye bye.